So welcome to my presentation, Bernoulli principle, forces acting on lipid bilayers in the cardiovascular system. For sure, it might be a little bit misleading, the title. Nevertheless, I want to be a little bit more provocative, and you should understand that very well. Daniel Bernoulli is someone well connected in Basel, and at the end I will show you a slide where we have a new place that was opened very recently, so just 2 weeks ago here in Basel by the European Physical Society. So if you are interested in to see that site, please be free to see that. And this presentation is together with my clinical partner, Till Sachser from University of Geneva. He has also his own practice, and his background is in emergency medicine, inner medicine, and cardiovascular medicine. Yeah, the clinical challenges are always the driving force for my kind of research, and Till has offered me such a possibility more than 10 years ago, and he was working in a certain setting and also using the emergency car of a hospital and treated patients who were affected by stroke and heart attack. And the only thing he could do is to provide vasodilator such as nitroglycerin. But the dose was very much limited because of side effects, and the dose is a very critical issue, especially having in mind that we are looking for a 1 centimeter stenosis maybe, that is critical, and the blood vessel system of a single human body corresponds to 10 to the 8 meters. That means 2.5 times around the globe. So a huge length where you are looking for just a centimeter, and therefore the systemic application of a well-known drug is hardly efficient, and that is a critical thing. So therefore we wanted to look, can we go from the systemic application of a vasodilator to a targeted delivery? And here we were thinking about nanocontainers that can transport the cargo and release it at the constriction. And we recognized that atherosclerosis is an inflammatory reaction of the body, and inflammation takes part at different parts of the body. So therefore, biochemical approaches seems to be less effective than maybe other ones. And because my background is physics, I was thinking about physical triggers. And one of the physical triggers could be the shear stress that is increased within the constriction. You see here on the top Maggie Holme, who is now a professor in Sweden, and at that time she was a doctoral student here, and she has also already presented at Clinam successfully some of the results. And the shear stress is clearly shown as an impact, especially because it is indirectly proportional to the vessel radius cube, and that has a drastic effect. For sure, we cannot rely on data in textbooks, as you see on the left, but have to know what is the situation within the body, and therefore Maggie also made visible atherosclerotic blood vessels using computed tomography with micrometer resolution. These data were also used by a colleague of mine from the Institute of Physiology at the University of Zurich, and Vartan is a specialist to deal with flow simulation, and what he was able to demonstrate is that we have a higher average wall shear stress at the constrictions, and that is not present at the bifurcations, as many reviewers have pointed out. Later on, Marzia, also a PhD student in my team from Italy, has continued that kind of research, and we were able to go even into more detail when it was done by the early experiments by Maggie. And Marzia was also the person who have studied the bilayer of these liposomes that we wanted to use for containers of nanometer size to transport the cargo. And we wanted to rely on natural lipids because that is easier than to go through all the necessary steps towards the patient. But we recognize that it's not so easy. So DPPC, for example, one of the well-known liposomal lipids, does not form interdigitation and therefore is too stable that the physical forces can open it. And that was demonstrated rather recently using small angle X-ray scattering with spatial resolution at the Allschwil Institute and also at the ESRF in Grenoble. The idea was then to take advantage of something that was theoretically predicted, as you see on the top, and we wanted to have something that is non-spherical. I have to excuse the image on the right is not the one what I intended to have, but okay, it does show that there could be some disorder and then faceted liposomes can be formed, as here demonstrated by Dr. Weinberger as one of the examples. There are many other teams worldwide who are able to produce non-spherical liposomes that are less stable than the spherical ones. And these liposomes can be generated through the interdigitation. You see on the top that we have a non-interdigitated liposome. That means something that has a thicker bilayer. And by starting the interdigitation, we make everything a little bit stiffer. And by increasing the stiffness, we can produce artificial phosphate lipid-based faceted liposomes. And you can imagine, for example, if you have a piece of paper, you can bend it easily in one direction, but to form a sphere is rather impossible. And the same principle has been used here for these interdigitated liposomes. These liposomes had been shown. I think mainly the team of the former Professor Zumbühl has shown that. And you see on the right-hand side an image from transmission electron microscopy that it is possible to produce these metastable faceted liposomes that show an appropriate diameter of about 100 nanometers, and they can release the cargo as intended. And that was demonstrated more than 10 years ago already in the thesis project of Maggie. Marzia has done a lot of important work in that field, and I mentioned already the spatial resolved small angle X-ray scattering we have performed at the Allschwil Institute here in Switzerland. It's a very interesting facility that helps us to measure the geometry of nanometer-sized entities. And here you see delta Q1 corresponds approximately to the range where the liposomes have their diameter. And on the right-hand side, you see this constriction. And within the constriction, nearby the wall, you see the increased values. And these increased values corresponds to an increased wall shear stress. So the wall shear stress is present and changes the size of the liposomes, really within the constriction. And one can even quantify it. It's about 6%. So it's not much, but it demonstrates that there is a force acting on the liposomes. Nevertheless, this is a small phenomenon, and we have also investigated the range of delta Q3 that corresponds to the thickness of the bilayer. So you see here again the flow from the left to the right, And you see that in the constriction, we have an increased wall shear stress, especially for the higher flow rates, but it is dominated by something else. You see in front of the constriction some high values, and also at the outlet you see some high values, and the question is, what is their origin? Because that is not the shear stress related. And that we found also from literature. So you see a part of the study on the lower hand that is based on some modeling, and above you see our data from the previous slide, and especially at the inlet you see a very similar behavior. This behavior can be explained by the Bernoulli principle. That means the pressure gradient force that is present at the inlet and the outlet. And that is something that is quite important, because you could imagine if we have an aneurysm or something like that, then it could also come to release of a vasodilator, and this make it hardly helpful. And therefore, I think we should have maybe have a look back, especially here in Basel. Dani Bernoulli was studying medicine first and earned a PhD degree in anatomy and botany here in Basel. Nevertheless, he is known as a Swiss mathematician and physicist. And after a while, he was trained also by his father and so forth, and switched from the chair of anatomy and botany via the chair of anatomy and physiology to the chair of physics. So he was really someone who wanted to go towards physics, and that is interesting. Also, from our point of view, he was rector of the University of Basel in 1744 and 1756. So you see, it was really a very important person for our city here. And I think you know many of these examples. He has revolutionized. Some of them are even described much later than his death. So airplane wings is something maybe is 100 years old, but not as old as the time when he was living. And I think airplane wings is not the only one, but you know also combustion, you know water-just vacuum pump, as I do from practical courses of students, and for sure the biologists know very well the hydrodynamic focusing that had been used, and everything is related to this pressure gradient forces. And these gradient pressure forces seem to play a quite important role, and that was pointed out by Lee and co-workers already in 2009, who have investigated the mechanical triggers of plug rupture, and have had a look already to this interplay. And they claimed that although the local high wall shear stress at stenosis may damage the endothelium and the fissure plug, the magnitude of wall shear stress is extremely small compared to the overloading on plug. Therefore, pressure may be the main mechanical trigger for plug rupture. And that is also my personal opinion here. With that, I like to summarize my talk. So liposomes can carry drugs. That is very well known from many researchers, also presented at this conference. The composition of liposomes corresponds to something like the cell membrane, so it's biomimetic. Self-assembly and stability of lipid bilayers result usually in spherical liposomes, but interdigitation as a structural change allows for the preparation of non-spherical metastable liposomes with tailored properties. And shear stress can change the shape of the faceted liposomes, as was demonstrated experimentally. But the pressure gradient forces can annihilate interdigitation, changing faceted liposomes to discs that I have not shown, but maybe on the next I will show it. And also the temperature increase, so another physical trigger can result in the loss of interdigitation, as demonstrated by another PhD student of my team, Sofia Matvikev, and she has shown that very nicely. And thereby you see that interdisciplinary approaches are necessary to solve medical challenges, and bio-inspired structures, here the self-assembled nanocontainers from artificial lipids, are key elements. And here you see that the temperature can be used as a stimulus. You see here Sophia, who is working in industry here in Basel now, and the temperature increase can result in the loss of interdigitation. We can also use other stimuli, as had been demonstrated by other researchers. For example, ultrasound is also something that can be used here. This study is based on small angle neutron scattering, also performed at the Paul Scherrer Institute here in Switzerland. And Sophia has given also interesting insights in this precision nanomedicine, and I was very happy that we got the cover of that journal in 2018. And with that, I'm at the end of my presentation. I'd like to thank all the people who have actively contributed. You have also the chance to see a two-wheeler this afternoon at this conference. And with that, I like to come to the final slide. I have mentioned at the beginning of my presentation about the Bernoulli plate you can find within Basel, and that was offered, I think, at the 25th of September this year. Thank you very much.